Okay, this particular problem is kind of challenging. We've got that complex eigenvalues. So I wanted to walk through a complete solution. So we set up our determinant just like usual, a minus lambda I equals 0, the determinant of that. And when I got here, rather than using quadratic formula, I just completed the square. It's usually quicker for solving a quadratic. So I move the 2 to the other side, take half the middle coefficient, which would be 1, add that to both sides. This is a perfect square trinomial factor. Take the square root of both sides. You can get the same thing using quadratic formula. Here are eigenvalues. -1 plus I, -1 minus I. Okay, now we actually only need one. When we have complex solutions, we only need one of the eigenvectors. So I went ahead and found two linearly independent eigenvectors, but I'm only going to use the first one. So we want a minus lambda I times the vector k to equal the vector 0. Now we got to be careful here because we've got, along the main diagonal, we're going to subtract lambda. So we're going to have 3 minus lambda, -5 minus lambda. But we need parentheses here. So that negative is going to distribute. We're going to get a +1 and a minus I there. And remember, when you're looking for an eigenvector, you don't have to solve a system of equations because any multiple of an eigenvector is still an eigenvector. You really only need the top vector, the top row times this vector. And then the second equation would give you just a multiple of that equation. So I didn't even bother writing down the second equation. And of course, I like triple checked my work. I had to redo this problem 2 or 3 times. It is a complicated problem. Okay, so we're going to take this guy times K1, 1 times K2, and that should just equal 0. Okay, so we'll add like terms here. We get 4 minus I times K1, move the K2 over. And now I like the swap coefficients method. Make this guy -1, make this guy 4 minus I. Okay, so we've got that eigenvector. And for fun, I went ahead and found the other eigenvector, which looks just like this guy, but we get a plus here. But we don't need it. We're never going to use this. Now, that means that, what's it mean to be an eigenvector? That means e to the eigenvalue times t times that eigenvector will be a solution. That's what it means to be an eigenvalue and an eigenvector. That was our whole assumption. That's why all this works. E raised to that eigenvalue times t times the eigenvector is a solution. So we're just going to use this guy. Whenever you have complex solutions, you just find one eigenvalue, his associated eigenvector, and now we have to use, so that's what I'm using, that eigenvalue, that eigenvector. We have to use Euler's formula. And recall the Euler's formula says whether or not you have a t here, this is always true. E to the a plus bi is e raised to the a, and then times t, because I have a t here, cosine of bt plus I sine of bt. So the real part goes in the e, the imaginary part goes inside your sine and cosine, and you get this I out front. And we've got a t here, so everybody gets multiplied by t. And remember, these are the arguments of your sine and cosine here. It's not cosine of b times t, it's cosine of bt. Okay, so here's what we have. This was our eigenvalue. So the real part's going to go up here in the exponential. Don't forget our t. Our imaginary part here, remember that's 1 times I. So we get cosine of 1t, sine of 1t, and the I comes along for the ride. Okay, so we just said, remember this is the whole point. X1 here is this exponential times this eigenvector. So here's that exponential written in sines and cosines times that eigenvector. Okay, now here's the tricky part. We want to we want to separate out our real part and our imaginary part. So we're going to multiply this scalar. This is not a vector. So we're not doing some kind of dot product here. We're not like taking this times the first and this times the second. This is just a scalar function. We're just going to distribute it, multiply top and bottom by this whole thing. So you can check all my arithmetic here. All of this stuff times -1 that goes on top. All of this stuff times 4 minus I. I'm going to have to do a little foiling there. And I could have, this would have been a lot cleaner if I just left the e to the -it out front and not distributed it to everybody. But for like completeness, I went ahead and did. So check all the details here. Make sure you believe this. Now, anybody that has all real stuff, no eyes whatsoever, we squish over on the left. So on the top, this is my real part. Everybody else has an eye. On the bottom, my real part will be that guy plus that guy. These two have eyes. And then separate out all my eyes. Yeah, I've got my negative there. So on top, here is my imaginary part, and on the bottom, this will be my imaginary part. So I guess for completeness here, that guy there, I don't want that to look like a fraction. Here's my real part. On the bottom, here's my imaginary part. And I factored the I out. Now, why do we do this? I mean, we were perfectly good here. If we don't care, if we wanted complex solutions, here's a complex solution. And then we'd find a linearly independent one using the other eigenvector. We could do that. We could have complex solutions, but we want real solutions. So it turns out, and like we'll just take this without proof, that this vector of real parts and this vector of imaginary parts without the I are linearly independent solutions. And we know from our theory of solutions, if we have two linearly independent solutions, we'll have a general solution once we tack on some constants. So we take that U there, all this stuff here, and that's our first solution times C1. And I did here factor out the e to the -it. And then this whole guy here without the I times C2, and again, factored out the e to the -it. Then we solve our initial value problem. So we were told here back at the beginning, x, which is just the top solution, and y is 0. Okay, so we're just going across the top here. E to the 0 was just 1. Cosine of 0 was 1. Sine of 0 was 0. So plugging in x, plug in t equals 0 to get x of 0. We just get negative, because of that negative there, C1 is supposed to equal -2. So C1 must be 2. And then across the bottom, again, e to the 0 is 0, cosine of 0 is 1, sine of 0 is 0. So all the sines will disappear, the cosines will become 1. We'll get 4C1, excuse me, minus C2 must equal 6. And we already had C1 was 2, so we just plug in, solve. We get C2 equals 2. So now we're going to go back up here. We're still not done. Plug in 2 for both C1 and C2 and see if we can get any like terms. And just all the way across the top, this is what we get for our X, or X1, we might sometimes call it. Not X1 vector, just X1 solution, X1. Then across the bottom, when I plug in 2 for C1 and C2, we're going to get some like terms here. You can check all my details. We get this, and we can see here that is the correct solution. We're looking at a student's attempt at the problem, and it looks like they made their eigenvalue, or maybe one of their eigenvectors, a little more complicated than they needed to. So they got an equivalent solution. It just looked a little nastier. Okay, and that's a good place to stop.